So this question tells us about a plane that's flying horizontally. So flying this direction first at this point, and it's 150 meters above level ground here. That's its initial y value. That's one way of putting it. It starts to descend. Now, P is at 5 kilometers, but we want everything to be in the same units, so think of that as 5,000 meters. Or if you want to show everything in kilometers, which in this question it kind of tells you to do in kilometers, that's 5 kilometers and this is 0.15 kilometers. So the initial y value, the initial x value, but it's negative because it's at this side of the y-axis. It lands just at the origin here, at the 0, 0 point. This is the function of its descent, okay, of this path. And it's saying x goes from -5 kilometers, makes sense, to 0 at the origin, makes sense. First question is to find the value of f derivative of x. Same thing as saying dy dx. Okay, when x is equal to -4. So let's have a look at the function. So I skipped this part. This is from the functions lesson where it just shows that d is equal to 0 and that c is equal to 0. So we just have this left of the function. Okay, so find the value of f prime x. So this is our function. Get the derivative of each term, so this term and this term. And you can use the differentiation tables, which say that you multiply by the power, so multiply by 2, and then subtract 1 from the power, so that goes to 1. Or from here, I mean, multiply by the power, so multiply by 3 and subtract 1, which goes to 2. In this case, multiply by the power, multiply by 2, subtract 1, which will just leave x. X to the power of x is the same thing as x to the power of 1, exact same thing. Now it asked us at -4, so just plug in the value of x, -4. So this is the slope of this graph, minus 0.0288, the slope of this graph at -4. So at this point here, -4, the slope of that kind of line, tangent line, is negative 0.0288, which makes sense because it's sloping down, so it should be negative. But it's not sloping down a lot. It's a very gradual decline, so it's not a big slope. It's not a large slope. Next part here, using your answer from part B1, find the angle at which the plane is descending when it is 4 kilometers from touchdown. So 4 kilometers from touchdown is here, where we got the slope. Now the angle you get from the slope, tan of that angle is equal to the slope. That's always true. Tan of the angle here is equal to the slope. So you know what the slope is. Now get tan inverse of this to get the angle. So tan inverse, tan -1. This button here. So tan inverse. See here? Of minus 0.0288. Okay, part C. Show that this point is a point of inflection. So point of inflection means it's not a maximum point, it's not a minimum point, but it's kind of changing direction. So it's like when a curve goes. Okay, so it's like it flattens out for a little bit, like that. It flattens out for a part. It doesn't go straight down, it flattens out for a bit before continuing in the same direction. So you can see this happens. It's hard to see, but you can see this happens. It's coming here, it flattens for a small bit and then goes down again. So at first, a really exaggerated version of this would be to draw it like this, down and then flatten out. But it's a much more discrete version of that. So it's hard to see visually, so we need to prove it mathematically. Now at a point of inflection, just like a turning point, f prime of x, the derivative of x, is equal to 0. So first we have to show that. So the derivative of x, we got that already from part B. And we're going to set this equal to 0. Now another way, and now to show it's a point of inflection, you get the second derivative and show that that equals 0. This isn't in the notes because sometimes this test fails. The more foolproof way to do it is to check the slope just before x, so like at minus 2.6, and just after x, like minus 2.4, and show that they're both in the same direction. So to show that for a point of inflection, it's not that it changed direction, that would be a turning point, that it's like it just paused for a while and then kept going. So that if you show that the slope before and after, like here, the slope here and the slope here are both negative, then you've showed it's a point of inflection. So that's another way, but this way is acceptable if it works. So that show that x is equal to negative 2.5. And now to find this value here, the y value, you plug it back into the original equation. So now you know what the value of x is. To get the y, you plug it into the original equation. Always to get the y coordinate, you have to put it back in the original equation. You won't get the right y coordinate from putting it into this. If you plug it into this, you just get the slope. If you plug it into this, you get the slope of the slope. You plug it into this, you get the y coordinate, the original equation. And sure enough, that equals 0.075, and this is your point. Okay? So, part D here. If xy is a point on the curve, verify that this point here is also a point on it. Verify means that you can use the information they've given you to prove it. So this is our function. And the easiest thing to do is to plug these values in. So plug these values in and show that if you plug this in, it equals this. So plug in minus x minus 5, work it out, put the like terms together, and you'll find it equals this. How did we convert to the y? Well, we saw all of this is just the negative of our function. So you can replace that whole thing with y, or negative y, because the signs are different. This is the tricky one. Find the image of this under symmetry. But it's not that tricky. Basically, you want to see what do I have to add to the x coordinate and to the y coordinate to get the point of inflection. What do I have to add? What changes do I have to make to get to this point of inflection? So to go from here to here and to go from here to here. So the easiest way to do it is to do this point minus this point. So minus 2.5 minus negative x negative 5. You'll get this value here. It's okay to have it in terms of x. And the same thing for the y. So this is what you add to each of these points to get this point. So then you do that again. You add that same amount because it's a symmetry. If this is our point of inflection, and this is our minus x minus 5 minus y plus 15, this is what we added to get here. And now we add the same thing to get the image, where this is like our line of symmetry, like a mirror. We have to add the same thing to go to make it equal and opposite, to make it look the same but on the other side of this mirror here. So you just add those amounts on again to the point of inflection. Minus 2.5 plus this, and 0.075 plus this. You'll get xy, which adds up, because we've showed they're both on the curves, so xy could be the image.